Now is the time for the invited talk. Our first invited talk is Dr. Michael Katz. He is a principal research scientist at IBM T.J. Watson Research Center. His primary research interests are in domain-independent planning and in integration of planning and RL. He was a program chair for ICAPS 2021 and currently serves as in the ICAPS Executive Council Board as a member. And he has received numerous awards for his research, including Influential Paper Award in 2023 and Best Dissertation Award in 2011 for his domain-independent planning solver. He has given tutorials on AI planning at AAAI, HCAI, ICAPS, and he frequently serves as AC, SPC for AAAI, HCAI, and ICAPS. He is the creator of a workshop and a workshop chair of the first edition of the workshop on planning in the era of large language model. It is a sister venue, and it is on the 25th of Feb. So please do attend that as well. March 3rd. 25th of March 3rd. The first day of the workshop.
Thank you, Harsha, for such an amazing introduction.
And I guess.
Okay, wonderful. Thank you again. As Harsha mentioned, I do a lot of planning, and recently, in the last 2 years or so, we have started to look at planning with language models, and this is an outcome of, or the first part of the outcome of this investigation. So as, this is a team effort. I'm the one presenting, but there are many others to this work, and some of them are here. So come to talk to us, and we are happy to discuss everything that is related to this. So let's start with what planning is, and you have heard today a lot about this, so I will not repeat. I just want to emphasize one thing. This is a subfield of AI that is focused on automating the decision-making process, right? So what we want to do, we want to come up with automated ways or partially automated ways of deriving a behavior that can be used in all those autonomous or semi-autonomous systems. Okay, this is important, right? This should be automated. We should be able to produce solutions that we can trust, right? Now, let's talk about the planning problem. Planning problem in general, I'm not going to discuss, and you have seen a lot of different various problems that Shirin presented. I will focus on a deterministic problem, on very simple, the most simple setting of planning, which we often refer to as classical. So here, like, this is the mathematical slide, okay? So we are talking about problems that can be represented as mathematically as finite and discrete state space, with one known initial state, a set of states, subsets of states that we deem to be goal states, a set of action or action labels with a subset of that can be specified per state as applicable, and a deterministic transition function that given a state and an action will give us the outcome state. With each of such transition, we associate a non-negative action cost. Okay, so this is a classical model, classical search or classical planning model, and each solution is a sequence of actions that takes us from the initial state to some goal state, and an optimal means minimizing the sum action costs. Okay, now you can think about these, that these are usually referred to as labeled transition systems. You can think of this as a labeled graph, right? So graph with labels, when per outgoing edges there is only one possible, there is no repetition of labels in the set of outgoing edges per state. Okay, so now these are often for practical problems, they are often too big to explicitly express. So if you could explicitly express that, then we could run one of the existing algorithms that find paths in a graph, in an explicit graph, like Dijkstra, for instance, would give us an optimal solution in n log e. But when we cannot explicitly represent it, we need to implicitly represent it somehow. So when one way of implicitly represent, the simplest way is a black box representation. When we have two functions, the first one is given a state will tell us whether it's a goal state or not. And the second one is given us a state will give us the pairs of action and state as immediate successors of that state. Okay, so this black box representation is sufficient to actually solve the problems using blind search. But you can do more. You can, if you have higher level representation, like in one of the planning languages, like PDDL, then you can use that in order to solve more efficiently and so on. Now, recently, we have started to solve problems that are not specified in a symbolic way in PDDL or with a black box, but in a natural language description, right? And I think we have seen a lot of examples of these problems. This one is a game of 24. I will talk about it later, right? So once you have that representation, we might want to either map it into the planning language or map it directly into the black box. The second one is the one that we will be focusing on this in this talk. Now, like I said, we have been looking at this for the last couple of years. And what happens in the last couple of years, there was a lot of work in the learning community about how to solve these planning problems with language models. And so the first one, and I only mentioned it, I'm not going to talk in detail about this, is given a planning problem, give me a plan, right? I will give you the description. You tell me exactly what to do from start to end. This really, Rao has been extensively talking about this. I recommend to listen to one of his lectures. I'm not going to talk about this. I'm going to talk about the other approaches that are kind of try to explore part of the search space of that label transition system that I've presented in the slide before, right? So there are approaches like chain of thought, reactive wood, that you have heard about this from some, for instance, right? And they kind of try to explore and generate a few paths and see whether they are able to find a solution while doing that. Or there are approaches that perform a limited search with the help of existing algorithms, with modifying these algorithms a little bit, right? So these are approaches like tree of thought, RAP, plots, algorithm of thought, graph of thought, and many other things of thought. And they all do the same thing, right? More or less, they take the classical search algorithm and they use the language model during the search to generate successors, test whether the state is a goal state, check what is the estimate of a distance from the state to a goal, and so on. And they use that knowledge in order to guide the search, right? So, and then basically they find out that for sufficiently, well, for non-toy problems, it results in too many calls to the language model, so they start limiting the search algorithm, right? So how do they limit the search algorithm? They limit the branching factor of the search algorithm, they limit the depth of the search, they limit the number of these paths that they generate. They limit the size of the queue of the search. And in addition to that, they also put an overall total bound on the number of calls to the language model. And that results in particular algorithms that they suggest, propose for solving this problem, right? So this is what they have in common. Another thing that they have in common, they don't explore the properties of these algorithms. For instance, they don't check whether these algorithms are sound or complete or optimal, or they don't even present the computational complexity of these algorithms in terms of calls to the language models. So we did it for them, right? So basically, we try to see whether any of these algorithms are sound or complete. And we found that none of them are such. So they're unsound, incomplete solvers for solving planning problems, right? They have limited solution validation, so they present code that validates solutions, but no one validates that validator. And I will mention that soon. They report success rates of 70 to 80%, but no one reproduces the results of the previous one. They only compare to what reported in the paper, in the previous paper. And it seems like the success is measured by running this validator and seeing whether it gives you 0, 1. But it's not explicitly mentioned in the paper, so we don't really know. And of course, there is no computational complexity, as I said. So these are the numbers in terms of length of the depth bound, the number of rollouts, the branching factors bound, and the size of the beam bound, and so on. Now, let me ground it a little bit in an example. So the 24 game, as I mentioned before, it's a very simple game. You get a list of 4 numbers, and you need to find a way to get to a number 24 by performing a series of arithmetic operations, right? So anyone here did not, this is a simple game, right? No explanations needed. So this game has a really small search space, right? It's up to 4,500 states, more or less. And it's really clear how to search in that, right? So given a state, you can perform an operation, you get a new state, right? And so on. So the tree of thought, which is one of the most popular out of that set of papers, what they do, they perform a search using BFS search with some modification. And they get the successors by calling the language model at every step of the search. And they check whether the state is a dead end by calling the language model at every step of the search. So this is what they do, right? I will not go into details, but this is from their paper, right? So this is a call to the language model at every step of the search. They ask more or less the same question, okay, with different objects, basically, right? And then they plug it into this modification of the breadth-first search algorithm, which is limited somehow to produce solutions. Of course, the breadth-first search, the original breadth-first search, is optimal, right? It guarantees to produce optimal solutions. That does not. This does not guarantee to produce solutions at all, actually. So what they do that. They empirically show that this works better than chain of thought using the same approach. And in terms of getting a higher success rate, and they report accuracy of 74%. But to be honest, I don't really understand how. It seems that they're using a validator code that it's available in their repository, but also that validator code allows them to report 30% success rate on the only unsolvable instance that they have in their set. So in 30% of the cases, they were able to solve that unsolvable instance and report positive score on that. So can we do better? Or can we improve on this? So this is the point where we came with a very simple solution. So this solution is basically, let's forget all the fancy thing of planning. Let's focus on the things that we have learned in the first lecture of our Intro to AI class about search, right? So as I mentioned before, we have the search requires two functions in order to be performed. The first one is successor function. The second one is a goal test. So let's start by asking, oh, this is really small, right? Can you see anything here? So let's start by asking the language model to produce these functions, the code for these functions. Instead of asking the language models to produce successor every time, we can ask the language model to produce a code for a successor function, right? So given the description of this game, I'm just asking the language model, provide only the Python code that returns a list, of successor states for the state, right? And the language model predictably gives me this code. Now I can ask another question saying, provide only the Python code that tests whether a state is a goal state, right? And the language model gives me this code. Now what can I do? I can plug it into an existing breadth for search algorithm or depth for search algorithm or any other search algorithm and get a solution, right? Now, assuming that this code is correct, I will know that every solution that will be produced for every given correct input is correct, right? I don't need to validate every output of the language model or every output of the sequence of operations that gives me the 24. I just need to validate this and this, right? Now, in this work, we did that manually by basically saying, having a human expert to feedback the model on the code. So for instance, we had the language model produce a code for the game of 24 that disregarded that addition and multiplication are symmetric operations, right? And that it gave us addition successors for A plus B, but not for B plus A, right? For instance, right? So that would result in incomplete, but still sound successor functions. And that would potentially prevent us from finding a solution. So in such cases, we would a human would feedback the language model on saying something like, note that the addition and multiplications are symmetric operations. And the language model would then have the opportunity of augment or change the code and give us the new version. Now we have experimented with that. We run this loop 5 times. And in this, for this game, for instance, I will show results for other games as well. For this game, in 1.2 queries, on average, you obtain a valid successor function. One query is the minimum, right? So in one feedback was needed in one of the 5 cases, right? The goal test was always correct, by the way. So then the code that is produced can be validated and tested in general, right? And then you can deploy the solution, right? And when you deploy the solution, it actually does not include the language model at all, right? So you don't have the issues with deploying solutions that include language models, and there are lots of them. So, and then you can use, as I said, you can use various search algorithms as they are. You don't need to modify them. Why do you not need to modify them? Because we were able to solve the entire set of instances of the 24 game, for instance. There are 1,300 instances, if I remember correctly. We were all of them together. We were able to solve in under 2 seconds, right? As opposed to hundreds of calls to the language model, which per instance that the previous approaches were doing, that would take you approximately 7 seconds per call. Any person that
the sound is because you are using successor function to select one of those. So how do you guarantee completeness?
How do I guarantee completeness? Here, I don't, only with the human feedback. I need to validate by myself that this function actually produces all the possible successors of the state. I will get to that. Okay, so okay, time very good. Okay, so let's maybe go a little bit faster because I want to get to interesting to other interesting stuff. So okay, these things I already said. So you can plug it now into the search algorithm, right? So you get the successor function, you put it here. This is the BFS, right? The BFS as we know it. You put the goal test in, you put state representation. Here we just use stringify, Python stringify for state, whether it's set, list, dictionary. And then you can run the search and that's it. You're done. So we have explored this on 4 different domains. The 24 game, as I said, the crossword puzzle, the block sword that everyone knows, and the Pronto QA dataset. In all of them, you get 100% accuracy. In the end, you get it with a very small number of calls to the language model. So this is this is 2.2 here, 3.8 for crossword puzzle, 3.8 for block sword, and 2.6 calls to the language model on average for the entire domain, right? And here you can see a comparison between for the existing. So this is the theoretical investigation only. This is a comparison of the portion of the state space that these methods explore versus the number of calls to the language models that they produce, right? In order to explore that. And you see mind-boggling numbers, right? I mean, sometimes you make, I don't know, hundreds of thousand calls and you explore a small portion, and sometimes you explore 10 times the state space, right? With millions of calls. This is what these algorithms are actually doing. Yes.
To calculate the complexity of the algorithm output by the any way we need to run that.
Of course, you need to run the search, but as I said, so 1,362 instances of the game of 24. When I run the BFS search, right, with the generated models, it ends in 2 seconds. This is less time than a single call to the language model. And it's a comparable energy consumption. Yeah, but it's still incomparable. Right here as well, right? Oh, I don't know what they did. Yeah, okay. So in other cases as well, right? So you run the search, right? There is an overhead of running the search, right? That there is, right? The overhead remains there as well. Right, so the call to the successor function, the goal test is not the only thing that you do in the search, right? The rest remains. Okay. So now we got to this limitation of having the human in the loop, right? that actually need to feedback on the correctness of the code, right? And this is a huge limitation, right? It's this assumption is the first one that we need to relax, right? So in this work, automating total search, we wanted to relax this assumption and take the human out of the loop. The human will still be needed in order to provide some information that can be used in order to validate the code. So what we did basically, we said, instead of having the human in the loop feedbacking on the code that was produced, we will have a human pre-interaction with the language model to produce a few an information that we can use in order to create a few unit tests that then we can run on the code that is produced. Right now, the human interaction ends at the beginning of the process. And then we have a loop that interacts with the language model, asks the language models for the code, runs the unit tests on the code, and then feedbacks the language model automatically on the quality of the code from these unit tests. Now, what do we do? Specifically for the game of 24, we have 3 types of unit tests. The first one presents us with examples of goal tests and goal states and non-goal states, and we are using it to check whether the goal function is answering correctly on these tests. Right? We have an example of successor states and their successors, right? And we have, in addition, we have a partial soundness test that will tell us whether this cases where this particular successor or this particular state and another state is not a valid pair, right? So this T is not a valid successor of S, right? We cannot capture everything, but we can capture simple cases. Like for instance, in the game of 24, when the state is represented by a list of numbers, then the immediate successor has to be a list of numbers of size exactly 1 less, right? And that is something that we can test, right? This is a simple input that the human can produce, and we can take this input and integrate it into automated tests that we can give to the model. Now, the search actually gets a little bit larger because you now start with the BFS and introduce these in a few places in the BFS, these tests, right? So this is still a standard BFS, but with the insertions of these tests. Another thing that we, you probably don't see it here because it's really small, but another thing that we test is some domain independent tests. Like for instance, we can test whether the successor function does not change the state, right? The input state. So what we have seen in the previous work in some cases, that the successor function will write the successor, create a successor based on copying the given input state and changing it, right? So given that copy, it would modify only part of the state, which is a convenient way of creating successor. Only we need to know that in Python, a shallow copy will not modify the object, right? And the deep copy is required. When the shallow copy was performed, we would see that the input state would be changed. So this is something that you can easily check, and you can feedback on that. Okay, I see that I'm at the end of my time. Then I'm gonna skip over a few of these things and go to the experiments. So we have run on the 4 domains that from the previous work, and another domain, which is a Sokoban game. We have compared it, run on the multiple language models now, and not just GPT-4 that we did before. And you can see that the number of feedback interactions increases, but not significantly, right? This is still a very small, constant number of iterations, right? And constant because it's amortized per domain, right? This is done once per domain. Now we have partitioned it over the goal test, the successor test, and the successor the soundness and completeness test. Okay, and we can see how this differs between different models. The another thing that I want to show, and this will take half a minute, is that you don't have to do this partial soundness test. And without the partial soundness test, the results are the dotted lines, right? So basically, you can see that even without the partial soundness test, from the first iteration where no feedback was done, to the last iteration when the sound and complete according to our test code is produced, we get huge improvements in the quality. Now I will skip over the error partitioning, and I will just take us to the future work. So in the future work, we were thinking of going beyond the blind search, which might be not as efficient for larger problems, and doing something like deriving heuristic functions. But Alex over there has already done that. And we were looking at things like search pruning techniques or duplicate detections, or deriving some invariants from the description of the playing problem in natural language and integrating them into search. We were thinking of how to further automate the tests and doing things like deriving the unit tests with the language models from the natural language description, and so on. And the last thing that I really need you to take home from this is this, right? So really be aware of the energy consumption of running these language models, right? If you need to perform hundreds of calls to the language model to solve a single task, and you need to repeat solving that single task many times, or doing lots of tasks, think again, right? Maybe language model is not the best way for solving that problem, right? There are immensely power hungry. Okay, that's it. I'm out of time. So thank you for this call, and I will take a few questions if I have time.
So I just want to summarize this. If I understand it. So what you're saying is that instead of making calls and whatever we want, what we can do is to ask for it in a chain of thought or automate a semicolon. Ask for it to run the code for us, and then run the code directly on the problem. And you see better results, or
instead of repeatedly asking for similar questions in a different seated with different objects, basically they are essentially the same questions. I can ask the LLM for the code for solving that, right? And then the main part is that code is what I need to validate, right? Once I validate that, I have a sound and complete solution.
yeah,
And that's guaranteed.
That is a lot there at the moment. So is there an automated framework, or
so I don't get the guarantees with unit tests, but this is what we get with software development in general, right? Right? We have unit tests if this is our proxy to the correctness of the code, right?
Yeah.
The better unit test you have, the better your code is.
Thank you.
Do we have time for one more?
So it shows like a Python, like this imperative programming for representing these items. So why not using something like declarative, like LLM-based? So it's a generality, expressivity.
Mm-hmm. So let's take the 24 game as an example, right? Can you write a PDDL description for a game of 24 without numeric fluence?
Yeah, you mean fluence, yeah.
Right. So, I mean, there are other features that are not easy to represent in PDDL, right? With black box successor functions, we can represent well, much more. I don't know what's going on here. So,
Yeah,
yeah, so something is changing here.
yes. We're preparing for the next round.
Okay, cool. So that, I hope that answers your question.
Yeah, I mean, thank you.
Thank you.